Now, I want to spend a few minutes on what will be considered as part of Chapter 7. Okay, Chapter 7 is a chapter on filter design. Okay, we are not going to be spending substantial portion, but I want you to have the basic fundamentals of filter design. So, Oppenheim and Schaefer, Chapter 7 deals with digital filter design. And I want you to have the basic concepts so that this will be a topic that you can always refer to and use it whenever there's a need. Okay, so here's sort of a quick background. Okay, filters, one of the most important applications, building blocks of a discrete time processing system. Okay, this is a very important building block of discrete time systems. Building block. Okay, the entire premise of a filter is frequency selective. That means it treats different frequencies differently. Okay, so some frequencies are amplified. Okay, some frequencies are attenuated. So, if you want to completely remove a particular frequency, then you want to make the attenuation infinity. And typically, we are not looking to add, boost the signal. We just want to say, am I allowing this frequency to pass through, or am I attenuating the signal? So, we can, as we have looked at, filters are LTI systems. Okay, these are LTI systems and they are represented by means of an impulse response. There is a transfer function h of z. Okay, now the most general LTI system will be a rational transfer function. So, the filter can be either an infinite impulse response or it can be a finite impulse response. Okay, and the advantage of the finite impulse response is that we can design it very easily to have linear phase, or we can design it to have minimum phase. Both of these are important properties that we know how to do. Of course, we can do it for the IIR also, but we cannot get linear phase. We can get minimum phase, but IIR linear phase is not possible. Okay, so when you look at filters, what are the basic specifications of a filter? Okay, I want you to look at that particular aspect. Okay, so let us see if we can enlarge these two. Okay, and keep some space for writing. Okay. Okay. So, on the left hand side, we have the filter specifications. And we have written it in terms of a low pass filter. Okay, we can generalize it to any other. So, the first thing is to indicate what is the pass band. What are the frequencies that you want to pass 0 to omega p? What are the frequencies that you want to attenuate? Stop band. That will be omega s to pi. It's real coefficients, so therefore the magnitude response, phase response, everything will be, will repeat, so we don't need to. So, given this, we then have a transition band. Okay, transition band, where you basically are going from the frequencies that are allowed to pass through and the frequencies that are attenuated. The transition band starts at omega p and ends at omega s. Okay, and now within the pass band, you allow the gain of the filter to be, ideally you would like it to be 1, but again this is a filter with finite number of coefficients, so basically the frequency response will not be constant, it will have some variation. You want it to vary between the value of delta 1 on either side of 1. So 1 plus delta 1 is the maximum, 1 minus delta 1. This is the pass band ripple. So delta 1 is what we call as the pass band ripple. The variation that you see, ideally you want it to be 1, the variation that you see. Similarly, delta 2 is the stop band ripple or the stop band attenuation. Stop band attenuation. Okay, this is what is the minimum attenuation that you want to see for your signals that are in the stop band. Okay, so what are the design parameters? Here are the 4 design parameters that we will specify for any filter, particularly for a low pass filter. We know that it always starts at 0. We have to specify omega p. This is the pass band edge of the pass band. Pass band edge, and it is specified in radians. Okay, omega s is the stop band edge. This is also specified in radians. Okay, and you have to specify what is delta 1, what is delta 2. And sometimes you may specify delta 2 on a dB scale. It is called as the attenuation, and it is given as minus 20 logarithm base 10 of delta 2. So basically this will be in dB. Sometimes you will hear people say the attenuation of this filter is 60 dB or the attenuation of this filter is 80 dB. So basically that's the representation that we have. Okay, and basically what I want you to think of is when you go through the design and then you check whether you have satisfied the specifications. If you have a design which has got, after you have done the design, this is the magnitude response, okay, as a function of omega between 0 and pi. So did it satisfy omega p? Yes. Up to from 0 to omega p, it was between 1 plus delta 1 and 1 minus delta 1, no problem. So at the edge it crossed, but that is allowed. Okay. Similarly, did it stay between minus delta 2 and delta 2 in the stop band? Okay, and that also is satisfied. So we satisfied the pass band edge, we've satisfied the stop band edge, we satisfied the ripple in the pass band, ripple in the stop band, all. So this filter meets the specifications. Meets all specifications. Okay, and now you ask the question, is this filter that we have designed, is it optimal? Okay, optimal in the sense that obviously this is a FIR filter with order, FIR filter which has got order equal to m, it has got length equal to m plus 1. Okay, is the filter optimal? Filter optimal with respect to the length of the filter. Okay, whatever length you have taken, is it the minimum possible to meet these specifications? Is the filter optimal in terms of length of the filter? We have met the specifications, length of the filter. Okay, very, very important question. And of course, the answer to this comes from the filter design theory, which is there presented very nicely in chapter 7 of Oppenheim and Schaefer. It says this filter is not optimum. Now, how do you know by looking at it whether it is optimum or not? The recognition is that you see that there are portions where the specifications are over satisfied. right? You're allowed delta 2, but you have the variation is limited to less than delta 2. So you can point to this and say specifications over satisfied. Specifications over satisfied. Okay. Then you ask the question, how will you make sure that the specifications are exactly satisfied? Okay. The answer is, if you had designed a filter whose response looked like this, basically whatever variation was allowed, you made sure that it was meeting these. So here is a filter that will be optimal. Okay, optimal. And what is the condition for optimality? These ripples are of the same amplitude. So these are called as equi-ripple filters. Equi-ripple filters. Okay, and it turns out we have a software program called the Parkes-McClellan. Parkes-McClellan software. Okay, it's there in MATLAB, it's there available in open source. Parkes-McClellan algorithm, which will design for you a filter that has this type of behavior. Okay, amazingly powerful tool. It has been used for more than 4 decades. It's one of the most widely used software in discrete time signal processing. Okay, so what are the inputs that you would have to give to a Parkes-McClellan filter? Exactly what we had talked about. Okay, what is omega p? What is omega s? These two can be combined to give as a single parameter, which is called the transition band. Okay, what is the transition band? Transition band, it is omega s minus omega p. Basically, it is given in radians. Okay, and then you must specify what is delta 1, what is delta 2. And once you have specified this, the last thing that you will need to do is to specify the order of the filter, M. And once you have given these combination of these constraints, then you will get a design which will give you the specifications that we have. Okay. Now there is a useful tool that you should always keep in mind, and this is the estimation of the filter order. To know what is the filter order that you will need for a particular specification that you have. Estimation of filter order. This is for Parkes-McClellan filter design or equi-ripple filter design. Okay, this is identical to equi-ripple filter design, optimal. Equi-ripple. So the formula that is given says that the filter order M, right? That is the order of the filter. So this is filter order is equal to minus 10 logarithm base 10 of delta 1 multiplied with delta 2 minus 13 divided by 2.324 times delta omega. Okay. Now, before we even look at it very carefully, I want you to look at the implications of it. Now, if you want delta 1 to become smaller, less variation, okay, smaller log negative of it, so therefore this becomes a larger number, filter order will increase. So here is the observation, M will increase if delta 1 decreases or delta 2 decreases. You tighten the specification of the filter in terms of passband ripple or stopband ripple, you must expect to have a larger filter order. Okay, very simple. Similarly, if you tighten the filter specification in terms of the transition, the passband to stopband, if you want to make it a very sharp filter, delta W will become smaller. The filter order will increase. So M will increase if delta W decreases. So any time you tighten the filter specification, the order is going to increase. So let us take an example. Okay, example. Supposing I give you the following specifications. Delta 1 is equal to 0.001 or 0.1. Okay, delta 2 is equal to 0.001 and delta omega is equal to 0.2 pi. Okay, and how did we get this? Omega p we can specify, we've specified as 0.4 pi, omega s as 0.6 pi. It's a low pass filter, these are the specifications. So given these conditions, please try it out on your calculator. You will get m about 25 point something. You have to take it as the next higher number, take it as 26. Okay. Case 2. Everything same except delta 2 is now 0.0001. Okay. If you were to write this in dB, this will come out to be 60 dB will be the AS attenuation. In this case, the stop band attenuation will come out to be 80 dB stop band attenuation. Okay. So we have increased or tightened the specification. What you will find is that if you do the same calculation, everything else same, M comes out to be 52. So you must have a longer filter in order to be able to satisfy these conditions. Okay. Now, if you, in case you are wondering, how do you get omega p, omega s, all of that is good in discrete time domain. But if you are dealing with conversion from a practical system, so let us look at a practical system. Okay, a practical example. A practical example. Okay, so we have a system where we want the pass band, a low pass filter. Pass band should pass all frequencies between 0 to 2 kilohertz to 2000 hertz. Okay. And we want delta 1 to be 0.01. That's the maximum ripple that you want to do. And the stop band, any frequency greater than 3000 hertz. Okay, so basically it's an analog, continuous time system where you want to pass frequencies between 0 to 2000 hertz. You want to stop all frequencies above 3000 hertz. So and again we want the delta 2 to be 0.001 as the gain. So now remember we are talking about a discrete time system. So we must choose a sampling frequency. Sampling frequency must be greater than twice the highest frequency component. This is 3000. So we're going to choose a sampling frequency of 10,000 hertz. Okay, which means that you must also use an anti-aliasing filter. Remember, before you do any sampling, you must have an anti-aliasing filter. Anti-aliasing filter, we should have a cutoff which is at 5 kilohertz. This is an analog filter. Make sure you satisfy, you pass it through and make sure that there is no aliasing. Okay, so now given these conditions, what is omega p? So omega p will be equal to 2 pi times 2000 divided by 10,000. Okay, so this is 0.4 pi. What is omega s? 3000 hertz. So 2 pi into 3000 divided by 10,000, that's your sampling frequency. So this is 0.6 pi. Okay. So you can see that whatever the values that we took in the example that we considered actually come from this practical example where we were looking at allowing frequencies up to 2000 to pass through frequencies above 3000 to be cut off, anti-aliasing filter with a bandwidth of 500 hertz, 5000 hertz, and sampling frequency of 10 kilohertz. So again, this is the way you would take the requirement, then design the digital filter and apply it on the sampled signal. So therefore, you are then able to achieve the desired processing of the signal in the discrete domain. Okay, let me conclude today's or this part of the presentation with a example of Parkes-McClellan's design. Okay, this is something that I would like you to try out with some software, and Mr. Tony will guide you to find where you can get access to the software, or we can help you with that. So the Parkes-McClellan, we're going to give the inputs omega p equal to 0.4 pi, omega s to be equal to 0.6 pi, again same as what we were looking at. Now take delta 1 to be equal to 0.009. Okay. And basically delta 2 to be equal to 1/10 of that. Okay, so you want delta 2 to be 0.0009. Okay, then you do the filter estimation. It comes out that m is approximately 26, and you can look at the impulse response. M is even. So you will have a middle tap around which you will have. So this is the point of symmetry. Point of symmetry. Okay, verify that you get the corresponding symmetry. Okay, that's point number 1. Second, go in and zoom and verify that you get equiripple. It should be equiripple in the pass band and in the stop band. So when you plot the magnitude response, you can easily see the stop band will have equiripple, but the pass band you will have to zoom in to see. Okay. And finally, make sure that this particular filter design has also satisfied the condition specifications for delta 1 and delta 2 that we have given.